Welcome to the Unit 4 Session 2 of our Financial Modeling course. In this session, we are going to continue with our test of autocorrelation or serial correlation, and here we are going to focus on a formal test other than using the plot or a simple plot. So by the end of this session, you should be able to understand and explain the Durbin-Watson test, and also you should empirically be able to test for autocorrelation or serial correlation using financial data. The Durbin-Watson test or the DW test. The Durbin-Watson test or statistical test is an important diagnostic tool for checking serial correlation in the residuals of any regression model. So earlier on we were testing for, or we were finding serial correlation using plots, but here we are going to test for the existence of serial correlation or autocorrelation within our regression model by the use of Durbin-Watson test. So Durbin-Watson test is a test for the first order autocorrelation. So unlike the other tests like the Bruce, Geoffrey, or the Lunchbox test, among others, here we are only testing for the existence of first order autocorrelation. So it is designed to detect the autocorrelation of the form in equation 3.32. So this is our residual and this is our stochastic error term. So we are modeling for the residuals, and we are saying that the p or this sign, which is epsilon, it represents the correlation coefficient. So we are saying that we are looking at the correlation coefficient in the error term plus the stochastic, in the residuals plus the stochastic error term, which is a random term. So this is an AR model, which is, this indicates that we are only looking at the first order correlation because we are looking at autoregressive model, but we're only focusing on the one lag, so which makes it the first order autocorrelation, or we are considering the first order autocorrelation. The null hypothesis of the Durbin-Watson test is that there is no autocorrelation within the error term. So here we are saying that the correlation coefficient is equal to 0. That is the null hypothesis. But the alternate is saying the opposite, which is that the correlation coefficient is not equal to 0. So when we reject the null hypothesis, then we are confirming that there is autocorrelation among the residuals of the regression model. So the Durbin-Watson is given as follows. So the D, which represents the estimate of the Durbin-Watson, because we have earlier said that a hat on any variable or any parameter indicate that is an estimate. So the Durbin-Watson test goes, or is being estimated using the model in equation 3.34, where the epsilon hat is, or it represents the epsilon hat represent the residuals, that is the current residuals, and the epsilon hat t-1 is the previous day's error term. And these are simply the models that we are using in estimating the Durbin-Watson. But because we are not going to do this manually, we will lay less emphasis on these models. Okay, so in approximated form, the Durbin-Watson looks like the equation 3.35, where dw is assigned to 2 into bracket 1 minus p with the epsilon, the current, and the previous epsilon. So in simple terms, we are saying that at the extremes, this is the 4 is, so the Durbin-Watson should fall between 4 and 0. So it can either be greater than or less equal to, it can either be greater than or equal to 0, or less than or and equal to 4. So at the extremes, this row symbol, which representing the correlation coefficient, is saying that when this value is equal to 0, when we get a value equal to 0, so when the correlation coefficient is actually equal to 0, then we will have a Durbin-Watson value of 2, which indicate that there is no autocorrelation. On the other hand, if this value gives, or if this value is equal to 1, and we have a perfect positive serial correlation, which indicates that there is the presence of autocorrelation within our regression model, and in this case the DW will give us a value of 0, and when the correlation coefficient is negative, then we say that, or it's equals -1, we say that there is negative perfect autocorrelation. So, and in this case the DW will give us a value of 4. So roughly speaking, we do not reject the null hypothesis if the W-Watson test is near 2. That is, there is little evidence of autocorrelation. So when the value is close to 2, we don't reject the null hypothesis, but we conclude that there is little evidence. So, but the W-Watson test has 2 critical values. That is an upper critical value and a lower critical value. So, and there is also an intermediate region where we neither reject nor fail to reject the null hypothesis. So with critical values, the null hypothesis is rejected, and the existence of positive autocorrelation presumed if the W-Watson test is less than the lower critical value. On the other hand, the null hypothesis is rejected and given that the value is negative, or one will presume that the W-Watson value is greater than 4 minus the lower critical value. In simple terms, the W-Watson test is when the W-Watson test is closer to 0, there is greater evidence of positive autocorrelation, and the closer that value is to 4, and the greater is the evidence of negative autocorrelation. If the DW or the W-Watson test is close to the value 2, then we are saying that there is no evidence of positive or negative autocorrelation. So here we are indecisive. So the value that we are going to obtain from the estimation of the W-Watson test will give us, or will help us in concluding as to whether we have the existence of autocorrelation or no autocorrelation. But our null hypothesis says that there is no autocorrelation, and the alternative is saying that there is autocorrelation. So the W-Watson test can be tested with the use of either the eViews, or you can test it with the use of IBM SPSS, among other analytical tools. Thank you once again for your attention as we meet to the end of today's discussion. Hope to meet you again in our next session. Stay blessed.